So this is a short presentation about the secondary scientific objectives of this mission. So it's essentially about things we still have to do and that have not started, but will keep us busy, I think, up to launch and probably beyond that, definitely. Just one or two clarifications. So these secondary species of ALTIUS, so of course, long time ago, it was foreseen that ALTIUS would do more than just ozone, but we were also dreaming of other instrument performance, characteristics, and so on. But it was always there. It has always been there. Today we have to live with the instrument which is there, and reality has applied some constraints to us, of course. So we have to deal with some limitations, and probably the biggest limitation is that definitely this instrument and this space segment is optimized for the primary scientific objectives. So actually the rules of the game are, there are probably things that we can do in addition, and we are going to investigate that very seriously. There are a number of other products that can be done, but we have to check if they are feasible in given observation modes. So not all species can be done in all observation modes, and you know that ALTIUS is good at providing different observation geometries and so on. And the design of the instrument is there, so we have to live with the basic parameters, and the most important ones are, of course, signal-to-noise ratio and spectral resolution. And that's basically what I wanted to show at the beginning of this presentation. So that was the situation we were dreaming about a long time ago. So a full range of wavelength. But today this is more what we have. And so you see the three bands. They represent the spectral coverage of the UV, visible, and near-infrared channels, with a nice overlap between the vis and the near, which I think will be interesting for consolidation of the results. And as I was saying, the most basic and most important parameters in order to determine what can be done in addition to ozone with this mission is probably signal-to-noise ratio and spectral resolution. So this is a view of the expected signal-to-noise ratio we will get in bright limb. So again, ALTIUS is a very flexible instrument, and there is flexibility also in the way you are going to bin the pixels, for instance, because we are taking spectral images. We have the flexibility to bin completely horizontally all the signal we get at each altitude, or we are just binning a portion of it. So this will influence the final signal-to-noise ratio we will get. And this is what you get when you just bin everything horizontally and not bin vertically. So we are quite, we have quite nice figures, I think, in terms of signal-to-noise ratio. We are hitting into the thousands, definitely. Of course, it's going to be more difficult in the UV, but I think we have quite significant values which give hope that there is something that can be seen from the data. And the other important parameter is the spectral resolution. And so there is one very funny one, which is the UV spectral resolution. It looks like it's my son who has made the slides, but so this is real. So this is really what the spectral resolution is going to be in the UV, because we have a stack of 4 Fabry-Perots, and so it depends on the modes and the spacing of the Fabry-Perots, and sometimes you switch to another mode of a regime of operation of the Fabry-Perots, and this influences the spectral resolution. For the vis and the near, at least these guys are behaving much more politely, and we have a nice regular increase of the spectral resolution. And actually, so these are the parameters we have, and these are all the additional species that we could try to do with ALTIUS. They all come from the mission requirement documents. So we have OCLO, BRO, the mesospheric ozone, the temperature, NO2, aerosols, NO3, and H2O. And you see, well, for those who are really, who have a good feeling about UV vis near and about spectral resolution, which is needed to do that or the other species, you can already get a feeling about how easy it's going to be or how tough it's going to be. And for instance, I would say that OCLO, BRO with a spectral resolution of 2-3 nanometer is not going to be easy, and on the other hand, aerosols or NO3 should be okay. Water vapor, we have good hopes, at least in occultation. For the temperature should be fine, and we thought all we could do to preserve a chance to do the NO2 by really keeping the spectral resolution as low as possible at the very beginning of the tuning range of the visible channel, so that we are still around 1.5 nanometer, which is at the limit, but we have good hopes that we can still make the NO2. So this table comes from the mission requirement documents. That was the full list. Of course, the first rows are for the primary scientific objectives of this mission. So the ozone NRT, the consolidated, and the polar one, they have slightly different requirements in terms of precision and accuracy. And then I will go through the different ones. So the first one is the mesospheric ozone, which we intend to do mostly in solar, lunar, and planetary occultations. As the spectral range of the UV channel is starting quite far in the UV, so we are able to get almost up to the top of the ozone absorption cross-section, so we will have the highest sensitivity possible for ozone. So we are quite confident that for the upper part of the atmosphere, we are going to be able to be very sensitive in occultation mode for the mesospheric ozone. For the NO2, we are really intending to try this in the 3 modes, so bright limb, and then solar occultations, and all the other occultations taking place at night. So as I said, there was quite a bit of efforts to look at what was really the minimum or the coarsest spectral resolution we could accept for this species. So we played with convolving the absorption cross-section. And of course, we related this spectral resolution with the signal-to-noise ratio, and we put some numbers. But in the end, well, it was clear that we needed to go into the thousands for the signal-to-noise ratio with the spectral resolution we are going to have. But in the end, I think we are making this. So we have a very strong signal-to-noise ratio in the VIS. And as I said, spectral resolution is kept at the bare minimum, so it should be feasible in all observation modes. Water vapor. So water vapor, okay, so the more easy thing will be for occultations, definitely. So we have good hopes that water vapor in solar and lunar occultations, like for SAGE, it's going to be feasible. And some of us in the team will have to spend 2 years trying to do this with a bright limb, because we don't have the spectral coverage which goes up to the really further away into the infrared. There was a study by Alexei, for instance, showing that it would be easier to do it with 1.3 micron, if I remember well, something like that. We don't have this one, so we'll have to use other bands of water vapor, which have been shown to be less optimal to retrieve water vapor in bright limb. But okay, this will be definitely a study which we commit to do, but we'll see if it's possible for bright limb. Methane is no longer part of the list because it was when we were dreaming of the very long spectral coverage. For aerosols, of course, this is going to be a product that will be done in all modes. So for the bright limb aspects, it's going to be University of Saskatchewan, which is going to deliver this the L2 product aerosols, and we are going to take over the occultation aerosols. So all occultation modes will provide aerosol extinction coefficient profiles. Without additional complexity or anything special with respect to ALTIUS. Then we have these two nice guys, the OCLO BRO. So this is probably going to be a challenge, but this is, well, we are going to try this one anyway. Of course, so OCLO will be restricted to lunar occultations. So these are the occultations at night, which will provide us with the highest signal-to-noise ratio, and this is definitely what we are going to need. We definitely need SNRs going into the 3,000, 4,000, but in lunar occultation, it should be feasible. And for BRO, well, we're going to try to do this in solar occultation. Of course, there will this diurnal variability, which will have to be taken into account. But yeah, it's going to be at least attempted. NO3 looks like one of the relatively easy ones. It's going to be done at night with the lunar occultations definitely, and potentially a few planets providing a nice signal. We are going to use, of course, the band around 660 nanometers, 660 nanometers. And in terms of SNR requirements, should be okay because the signature is relatively strong, so it should be fine. And for the temperature, we are going to do this probably in brightlim and in solar occultation. So in brightlim, it will depend on the quality of the absolute radiometric calibration that we will have. If we have a good one, we can try to implement the method, for instance, by Mr. Schies, who has demonstrated that this is definitely possible if we have this wavelength and they belong to our range. And for the solar occultation, we are going to use a technique which was developed already some time ago for the Aura instrument, which relies on the refraction of the atmosphere. So in total, ALTIUS can deliver, in addition to the primary scientific objectives, something like 8 additional products. Not all of them in all modes, as you have seen. But actually, this will give us quite some work because it will result in something like 16 additional processing chains. So of course, there are redundancies. For instance, the solar and stellar or planetary occultation chains, they are very similar. They use the same radiative transfer model, so we don't have to redevelop everything all the time. But still, they are going to be treated as independent processing chains, which have to be implemented in a proper way. And my final message is that I don't know if it's clear to everyone, but ALTIUS is quite special. It is a tunable instrument on a very flexible and agile platform. This is perhaps quite different from what we have seen before. So it means that we can make measurements at many wavelengths, but we have to think in advance. So we have to know not before we fly, but we have to know during the mission at which wavelength we want to do our measurement. So of course we have our baseline wavelength set at which we want to measure, but if another approach, another method requires another wavelength which is in our range, if we don't plan it, we don't measure it. So if you guys have ideas about things that can be done or other suggestions, other approach for ALTIUS, we are very happy to hear about it, because when it will come to define the observation plan for the mission and so on, we have to know and we have to prepare these wavelengths. So there is flexibility to add new observation modes, to add wavelengths and so on, but we have to know. So it's really important that the community is aware that ALTIUS can do other stuff, but we have to know in advance, and so please talk to us, talk to the people who are going to operate the mission so that we know what we have to put in our observations. And actually, I'm ahead of time, and that was my last slide. Okay.